The gap between building in Dataverse and architecting with Dataverse is not a skill issue, it is a thinking issue. Most organizations treat Dataverse like an expensive spreadsheet. They build one table per app. They copy data across 5 different places because it feels convenient in the moment. They scatter business logic across Power Automate flows, plugins, and business rules. Then they wonder why changing a single rule requires a treasure hunt through the entire environment. But here's what is happening underneath. A structural flaw is costing enterprises millions in maintenance and rework, yet almost nobody names it. Dataverse business skills isn't about clicking buttons or learning the latest feature. It means thinking relationally. It means designing systems that don't break when you scale from 100 users to 10,000. You need to build architectures where security is structural, not bolted on at the end. The goal is keeping business logic consistent across every single app that touches your data. By the end of this episode, you will understand the 3 pillars that separate architects from builders. You will see patterns that actually work at enterprise scale, and you will have a 90-day roadmap to prove that relational thinking works in your organization. The problem nobody names: grid thinking versus relational intelligence. There is a metaphor destroying enterprise Dataverse environments right now: the spreadsheet metaphor. When people think about Dataverse, they usually just think about tables. They see columns and rows. They add a column for every new requirement and create a new table for every new app. It feels intuitive and visual because you can see your data right in front of you. And it works until it doesn't. Imagine you have customer data in a table. The sales app needs extra customer attributes, so you add them. Then operations needs different data, so you add even more columns. Suddenly you are looking at 200 columns where some are used by sales, some by operations, and some by nobody at all. The table became a dumping ground. Then you build a second app. You ask yourself if it should use the same customer table, but it feels easier to just copy the data into a new table for that specific app. Now your customer information lives in 2 places. When an account number changes, you have to update both tables, but you eventually forget the third table where that data also lives. 1 version is right, 3 versions are wrong. You have conflicting versions of the truth. This is grid thinking. It feels like organization, but in reality, it is just chaos. Relational intelligence starts with a different question. It isn't, where do I put this? It is, what business concept does this represent, and what else does it connect to? Building 1 table per app is a strategy that scales directly into failure. When you hit 1,000 users, the maintenance will crush you because you aren't maintaining 1 app anymore. You are maintaining dozens of copies of similar logic, data, and security rules. The cost stays hidden until it becomes impossible to ignore. It hides in your development time when a 2-week project takes 6 weeks because you are untangling conflicting structures. It hides in maintenance when you spend 2 days every month just reconciling duplicate account numbers. It hides in the decisions you can't make because you don't know which version of the data is actually correct. The problem becomes visible the moment you need a fundamental change. A single security rule might affect 5 different apps, but your business logic is scattered across flows, calculated columns, and plugins. You change it once and forget the other 3 spots, so the system breaks silently. The moment arrives when a system built for 100 users halts at 1,000. This doesn't happen because Dataverse can't handle the load. It happens because the architecture never learned how to think relationally about scale. Transition. This isn't a technical failure, it is an architectural one, and it all starts with how you think about your data. The 3 structural flaws. Flaw 1. Data duplication as the root cause. When you are building apps at high speed, duplicating data feels like a clever shortcut, but in reality, it is just debt that grows until you can no longer pay it off. Your main CRM table holds all your customer information, but then the sales team builds their own app and copies names, IDs, and account statuses into a separate table because it makes their queries faster. Operations follow suit with their own version, and by the 6-month mark, you have 5 different tables all claiming to hold the same customer data. At that point, you no longer have a single source of truth, or worse, you have 5 competing versions of it. Imagine an account number was typed incorrectly 2 years ago and finally gets caught. It fixes the mistake in 1 table, but finance is still pulling reports from a different one, leading to a week-long argument between departments about who actually has the right numbers. The reality is that neither of them is right because they are both looking at outdated, disconnected versions of the same exact concept. This is the moment where a single source of truth stops being a corporate philosophy and becomes a requirement for survival. When your customer information has 1 definition and 1 owner in 1 location, you change it once and that change flows everywhere instantly. Duplication does the opposite by forcing you to manage 5 different versions while hoping they somehow stay in sync. The cost of trying to reconcile these differences is massive. I have seen finance teams spend 2 full days every single month just cross-checking account numbers and status flags across 3 different tables. They end up building manual spreadsheets to bridge the gaps, and when those spreadsheets inevitably break, the entire month-end close gets delayed. That isn't a data problem, it is an architectural failure that creates endless manual work for your people. Audit risks also start building up where you can't see them. When an auditor asks you to prove a decision was made using correct data, and your answer is, it depends on which table you look at, you are inviting a much deeper compliance investigation. Regulators see duplicate systems and immediately wonder which one is real, which triggers forensic reviews that shift your costs from simple reconciliation to massive auditor fees. Then you have the compliance violations that emerge out of nowhere. You might delete a customer's personal data to comply with a GDPR request in your primary table, but 6 months later, an old report pulls that same data from a secondary table where it still exists. You have violated a major regulation without even knowing it because your data was living in too many places at once. Flaw 2. Logic scattered across apps, flows, and forms. The rules that run your business should never exist in 5 different places at the same time. Take a simple order validation rule where an amount cannot exceed a customer's credit limit. In a messy system, that logic might live in a Power Automate flow, a plugin that triggers on a save, a calculated field on a form, and a business rule all at once. When that credit limit rule eventually needs to change, you have to go on a hunt to find every single spot where it was programmed. You might find the flow and update it, but 2 months later, you discover a calculated field was still using the old logic and approving orders that should have been blocked. You end up with a compliance issue that stayed hidden because the system didn't actually crash, it just diverged silently. This kind of brittleness is purely mechanical. When you build logic through a series of disconnected integrations, every piece of the puzzle depends on every other piece staying exactly the same forever. If one flow breaks, the processes downstream stop working without any warning, leaving apps waiting for data that is never going to arrive. Citizen developers often inherit these systems and try to fix a flow, completely unaware that their change now conflicts with logic hidden somewhere else. The real nightmare of maintenance isn't getting a rule right the first time, it is the impossible task of finding and updating every single instance of that rule simultaneously. Performance always takes a hit in these scenarios. An approval process that used to take 2 seconds now drags on for 12 because it is waiting on a chain of asynchronous flows, and eventually your users will just bypass the system entirely. Flaw 3. Security as an afterthought, not a design. Trying to bolt security onto the top of a flat, unorganized data model almost always fails in practice. You might design a support table that everyone starts building on, but then a new compliance mandate says staff can only see cases from their specific region. You try to add a security role to fix this, but because the underlying schema doesn't actually enforce regional boundaries, you are relying entirely on a filter. One small configuration mistake and suddenly everyone can see everything, or you over-adjust the role and now nobody can see anything at all. The system simply cannot enforce rules that the original design never anticipated. Row-level security is a beautiful thing when your data is structured to support it from day one. However, it becomes incredibly fragile when your architecture was never built to handle those kinds of permissions. The bad news usually arrives months later in an audit finding showing that sensitive data was accessible to the wrong users for weeks. The investigation into what went wrong takes months, and the cost to fix it is even higher, all because security was treated as a layer to apply later rather than a core design element. A healthcare organization I know learned this lesson the hard way after their post-launch security model was found to be in violation of HIPAA. Because their data wasn't structured to enforce the necessary privacy rules, they had to spend 9 months and 6 figures on a total redesign. Transition. These 3 flaws are not actually separate problems, but are instead symptoms of a single disease, which is the failure to think relationally. The shift from transactional to structural thinking. Developing relational intelligence begins by asking a completely different set of questions. Most people start with transactional thinking, which focuses on how to store a specific piece of information right now so they can launch the next app. They just want to put a customer name here and an account balance there and call the job finished. Relational thinking, however, asks how that piece of information relates to everything else in the ecosystem. You have to consider which other concepts depend on that customer data and which business processes are going to touch it. You need to know that when one value changes, every other part of the system that needs to know is actually informed. The difference here is purely architectural. A builder focuses on the transaction, but an architect focuses on the structure. An architect understands that customer isn't just a convenient place to store names and phone numbers, but is a fundamental business concept. It is the hub that connects your orders, invoices, support cases, and payment histories, and every one of those connections must be modeled correctly. When you start thinking structurally, you realize that a customer is never a simple thing. It is the intersection where all your different business processes meet. If you model that intersection poorly by duplicating tables or scattering rules across different apps, those processes are eventually going to crash into each other. You can find clarity by asking what business concept a table actually represents. If you have a table called temp customer, because you only needed it for one specific app, you aren't building a concept, you are just avoiding a difficult design choice. Likewise, a table called customer that has 300 fields for 50 different apps isn't a concept either. It is just a dumping ground for data. Relational thinking forces you to be honest about the actual concepts your business uses to operate. Once you name those concepts clearly, you can finally start modeling them in a way that works. This approach forces you to have difficult conversations with the business side of the house before you ever start building. You might find that sales uses the term account, while finance uses customer, and operations talks about a bill-to party. You have to figure out if these are the same thing or if they are truly different. Because if they are the same, you don't need 3 tables. These might sound like technical questions, but they are actually revealing whether your company even has a shared definition of what a customer is. Most organizations eventually discover they don't have one, and while that discovery is uncomfortable, it is the only way to build an architecture that can actually scale. The 4 dimensions of relational design. Relational intelligence is built on 4 specific dimensions, and if you miss even one of them, the entire system will eventually fail at scale. First is normalization. This is about removing redundancy without killing your performance. You want one customer record instead of 5 different copies, and you need one status definition rather than 7 variations scattered across different tables. It is about building a clean, intentional structure. Next, you have relationships. This means connecting your concepts correctly. The question isn't how many tables you can link together, but rather what the actual relationship is between those concepts in the real world. One customer has many orders, many employees work in one department, and a single product might belong in many different catalogs. These real-world connections determine how you model the data, so you must choose your logic based on how the business actually functions. Then come invariants. These are the rules that must never be broken. An order cannot exist without a customer, and an invoice cannot exist without an order. These are not just suggestions or best practices, they are structural requirements. Relational design enforces these rules at the data layer so that no app, flow, or form can ever violate them. Finally, there is integration. This is how data flows in and out without creating new silos. External systems push orders in, while your system exports fulfillment status back out, and the relationships must hold true across those boundaries. You won't have to reconcile data manually because the structure itself enforces consistency. If you skip any of these dimensions, failure is coming for you. Skip normalization and you are back to maintaining duplicates. But if you skip relationships, your logic stays scattered. Skip invariance and your data becomes unreliable. And if you skip integration, your systems will eventually become completely incompatible. The cost of not thinking relationally. The numbers here are stark. Organizations that lack relational intelligence spend 40% of their development time on rework. They aren't building new features or moving the needle, they are just fixing structural mistakes made months ago. When 2 apps collide on the same data, the fix usually takes 3 weeks of engineering time. 65% of enterprises now report that they simply do not trust their operational data. This isn't because the data was entered incorrectly by a human, but because the structure holding that data offers no guarantee of consistency. 73% of low-code projects fail specifically because of poor data design. It isn't a problem with complex logic or tool limitations, it is a total foundation failure. Audit findings continue to pile up with the same recurring theme. Companies cannot prove who made a specific decision because the data trail is broken, which isn't a paperwork problem, it is an architectural confession. The business impact compounds over time. Decisions are delayed because nobody knows which data is real, and compliance risk stays high because security was never designed into the structure. Innovation eventually stalls because the foundation simply cannot support it. Pillar 1. Entity mapping. The first skill that separates a true architect from a basic button clicker is entity mapping. This is the art of taking the absolute mess that comes out of business conversations and translating it into a clean, functional schema. When your stakeholders start talking about customers, accounts, prospects, and contacts, they are speaking loosely. They have years of experience using these terms, so they just assume you understand the distinction between them. But in reality, you don't. Not yet. Entity mapping forces you to ask exactly what business concept each word represents. You have to figure out if a prospect is just a contact you haven't converted yet, or if an account is fundamentally different from a customer. These questions sound simple on the surface, but they rarely are, mostly because the business itself might not have a clear answer. I've seen this play out in a real scenario where a sales team was trying to use 4 separate tables in Dataverse for customer, account, prospect, and contact. When I asked if these were 4 unique concepts or just variations of one thing, the team couldn't give me a straight answer. They actually argued for an hour. What emerged from that meeting was messy. Sometimes a customer and an account were the same thing, but other times they weren't. A contact was always a person, while an account was sometimes a company. That confusion eventually lives in your schema. You end up with 4 tables just because 4 different words exist, not because you actually have 4 distinct concepts to track. Entity mapping works differently because it starts with a diagnostic interview. You ask what unique identifier a record has, what other concepts it connects to, and who cares when that specific data point changes. Through those conversations, the patterns finally start to emerge. You realize a customer is a legal entity you can bill, while an account is a specific contract relationship with that customer. A contact is a person who works there, and a prospect is just a potential customer you haven't signed yet. Now you have 4 concepts with clear relationships. Your model can finally reflect reality instead of reflecting the team's internal confusion. This discovery process isn't just a theoretical exercise. You have to draw relationship diagrams to see where the logic breaks. You map a customer to an account because one customer has many accounts, and then you connect that account to a contact. When you visualize it this way, the inconsistencies jump out at you. If someone claims a prospect is a type of customer, you simply ask if they share the same attributes. And if the answer is no, then it isn't a type of customer. It's a stage in a process, and that requires a completely different modeling approach. This forces clarity before you ever start building. Most teams skip this step entirely, and they only discover they modeled the wrong thing after the app is finished. Fixing that mistake later can cost you months of rework. The biggest mistake is treating every single data point as if it's equally important. Every field feels vital when a stakeholder asks for it, but entity mapping forces you to prioritize. You have to decide which fields define the concept and which ones are just extra data the concept happens to collect. A customer must have a name and an ID to exist, but while a phone number is useful, it isn't defining. If the phone number changes, the customer is still the same customer. Normalization forces this clarity automatically. If you find yourself trying to store the same data in 2 different tables, you've failed the entity mapping test. Either those tables represent the same concept and should be merged, or they are different concepts and need to stay separate. When your mapping is correct, redundancy becomes impossible. The business outcome of this work arrives immediately. Development becomes significantly faster because your foundation is solid. When a new app needs customer data, you don't copy fields or create a new table. You simply reference the canonical customer table you already built. Your build time drops from 3 weeks down to 5 days, not because you're a genius, but because a good foundation stops you from repeating the same work over and over. Pillar 2, logic delegation. The second skill you need to master is understanding exactly where your logic belongs. Most organizations build their systems backward. They put UI validation in the forms and handle calculations in the flows, which creates a massive mess because every layer can be bypassed. If you change the form, the flow has no idea what happened. If you disable the flow, the form starts calculating the wrong numbers. Relational thinking inverts that entire mess. It dictates that logic should live exactly where the data lives, which keeps it as close to the truth as possible. You move your calculations and your validations away from the UI and down into the data layer itself. This distinction is critical because of performance. Server-side logic, like business rules, calculated fields, and plugins, all execute inside Dataverse. This means there is no network latency and no waiting around for external cloud services to wake up. In fact, server-side logic is 11 times faster than cloud flows for the exact same operations. It isn't just 10% faster, it is 11 times faster. A real scenario illustrates how much this actually impacts the user. One company I worked with had an approval process living entirely in Power Automate flows. When an order exceeded a credit limit, a flow would trigger to check the customer's credit and evaluate the amount. That whole process took 45 seconds, and the users constantly complained that the system felt slow. We eventually moved that logic into a plugin, which is just server-side code running inside Dataverse. It was the same logic and the same business rule, but the processing time dropped to 4 seconds. The difference wasn't the rule itself, the difference was where the rule was running. Cloud flows have to wait on network calls and service bus messages, but plugins execute directly inside the data engine. That isn't a matter of philosophy, it's a matter of physics. Understanding what belongs where requires you to use specific categories. Business rules that enforce invariance, like making sure an order doesn't exceed a credit limit, must stay server-side so they can't be bypassed. Calculated fields that pull values from related records or roll-up fields that aggregate child records also belong in the data layer. Any plugin that needs to execute at the exact same time a data change happens should be server-side. Power Automate is meant for a different kind of work. It handles orchestration across multiple systems and integration when you need to push data to external platforms. It's great for notifications like emails or Teams messages and for routing approvals to the right people. These operations naturally need more time, and they need to be asynchronous because they rely on external access. The mistake is using those flows for basic calculations. If your flow has to read an account just to check a credit limit, that is validation logic, and you need to move it. If you don't and the rule changes, you'll end up updating 10 different flows because your logic is scattered everywhere. Or worse, you'll miss 3 of those flows and the system will start behaving inconsistently. Proper delegation reverses that problem. When you change the rule once, it applies everywhere because it lives in one central place. Whether an order is created through a web app, a mobile app, or an API, it will always run the same validation. This happens because the validation is tied to the data layer rather than a specific interface. The governance outcome follows naturally from this setup. Your IT team can audit all business logic from a single location in the data layer. You don't have to go on a treasure hunt through 50 different flows just to wonder where a specific rule actually lives. Pillar 3, security as architecture. The third pillar is a mindset shift. Security is not a policy, it is structure. Most organizations try to bolt security on top of a finished model. They have the data, and then they try to wrap rules around it. You see this when a manager says users in the East region should only see East cases. The rule sounds simple, but the problem is that the data was never structured to enforce it. Everything changes when you apply relational thinking. Before you ever store a single row of data, you have to ask how access will be controlled. That answer has to shape the model itself. Row-level security and business unit segregation are architectural choices, not just IT policies. If your data doesn't naturally separate by business unit, then trying to force security onto it becomes fragile. You end up fighting the system to prevent access through complex rules instead of letting the data structure do the work. That isn't governance, that's managing by exception. A healthcare organization I know learned this the hard way. They built their entire model first, and then compliance stepped in with HIPAA requirements. They tried to add row-level security after the fact, but the data wasn't ready for it. Some records had region information while others were blank, which meant the security rules applied inconsistently across the system. They went live anyway, and auditors immediately found patient data visible to staff who had no business seeing it. It took a 9-month redesign and a 6-figure check to fix a mistake that should have been handled at the start. Design time security thinking is the only way to prevent that kind of disaster. If patient privacy depends on region segregation, you must structure the data around those regions from day one. If role-based access is the priority, the model has to capture those roles accurately. You can't just add rules and hope they stick. You have to design the system so the rules enforce themselves naturally. Achieving least privilege without creating bottlenecks requires intentional architecture. You want to give a user every permission they need to do their job, but you cannot give them access to data they don't. This balance doesn't happen by accident. A salesperson needs to see invoice history, but they definitely don't need to see competitor pricing. If your model treats all financial data as one big bucket, your security rules are forced into an all-or-nothing trap. You have to design differently by separating data based on who is supposed to see it. When you do this, the compliance conversation shifts. You stop trying to prove that you're trying to be secure and start proving that you actually are. You become audit ready from the first day because security is structural rather than an afterthought. Any change you make to the system tomorrow will automatically respect those boundaries because they are baked into the model itself. These 3 pillars have to work as a single unit. Entity mapping defines what you are building, while logic delegation puts the rules where they belong. Security as architecture ensures those access controls actually hold up under pressure. Together, they represent the thin line between a professional architecture and a lucky accident. What changes when you think architecturally? Moving from a builder to an architect isn't about making things more complex. It's a shift in your scope. A builder works vertically. They focus on one app and ask how to make it fast or how to hit a looming deadline. They want to know the absolute minimum they need to ship the product. These are important questions, and the builder role is necessary for getting things done. But an architect works horizontally. They realize that one app never exists in a vacuum. It is just one small piece of a much larger operating model. The questions change to how this new piece fits with everything else and what else might break when this new capability is added. This mindset shift reshapes every single decision you make. When a builder hears that sales needs to see customer credit history, they just add a field and finish the task in an hour. An architect hears that same request and pauses to ask better questions. They wonder if 3 other apps will eventually need that same credit history, or if the data needs to be synchronized across different systems. They look at whether the data is stable or if it needs to be refreshed constantly. The final solution might still be adding a field, but now that field is placed in context and built to scale. Architects are obsessed with reuse. They want a solution built once and used by many people across the organization. They design a schema for the customer concept as a whole, not just for one specific app's version of a customer. They build a security model that serves every application instead of bolting permissions onto each one individually. They centralize business rules so they aren't scattered across the environment. There is a very practical reason to make this shift. Architects usually command compensation that is 40 to 60% higher than builders. This isn't a reward for making things complicated. It is a recognition that architectural decisions have a massive ripple effect. A builder's choices only affect one app, but an architect's decisions affect the entire system. That leverage compounds over time. Relational thinking changes how you justify your time. A builder might say, a certain task will add 3 days to the launch date. An architect will point out that while it adds 3 days now, it saves 4 weeks of rework later when the next app needs that same data. Suddenly, the math on that decision looks very different to the business. Eventually, you reach a point where you stop defending your design and start explaining it. A builder justifies their work by saying they needed to move fast. An architect explains their design by pointing to the relationships and showing how the structure serves 5 different business processes at once. One person is defending a choice, while the other is articulating a principle. The architect's responsibility. Accountability shifts the moment you step into the role of an architect. You are no longer responsible for making sure a single app succeeds, but instead, you are responsible for ensuring the entire system doesn't fail because of the choices you made. Poor architectural decisions compound exactly like high-interest debt. A shortcut you take today, like promising to standardize a process later, usually costs 10 times more to fix just 6 months down the road. This happens because other apps start depending on that shortcut, and before you know it, multiple teams have built their entire workflow on top of a flawed foundation. The actual cost of change multiplies every time a new app touches that original mistake. This reality forces architects to say no much more often than they say yes. They aren't trying to be gatekeepers or stop progress, but they are responsible for the long-term consequences that the requesting teams simply cannot see yet. The real skill here is explaining why a shortcut will cost more later without sounding like you are just being difficult. You might tell a stakeholder that while you could build a feature in 2 weeks using a quick fix, taking 6 weeks to do it the right way is the better investment. You choose the longer path because when the finance department needs that same data in 3 months, the quick way would have forced 8 weeks of painful rework. That isn't killing innovation, it's protecting it. You are making decisions that future teams can build on top of, rather than having to find ways to build around. Trust in an architect builds from being right about the hard things. You don't have to be right every single time, but you need to be right about the heavy decisions that take months to prove out. When a team eventually admits they tried a shortcut and hit the exact wall you predicted half a year ago, that is how you earn real credibility. The business outcome is always the same. You see fewer emergency fixes as architectural debt shrinks, and you get more planned improvements because the foundation actually supports them. Skill development path, entity mapping. Learning how to map entities is a skill anyone can pick up. It doesn't require you to buy new tools, but it does require you to change the way you ask questions. Start exactly where you are right now by auditing your current Dataverse environment. Look at every single table and ask yourself why it exists. Don't look for a philosophical answer, but look for a practical one that defines what specific business concept that table represents. You will start to see patterns almost immediately. You might find 3 different tables that all hold customer information, and when you interview the teams, you'll find that sales, finance, and operations each built their own version. The reason for this is never that the data is fundamentally different, but it's almost always because one team needed it fast. Now you're stuck with 3 separate tables doing the exact same overlapping work. Identify this redundancy clearly by walking through your schema. Look for columns that appear in multiple tables and note where the same data is being stored in 5 different places. Write these findings down, not to point fingers or blame anyone, but so you can finally see the actual state of your system. Next, you need to map the relationships by drawing a functional diagram. It doesn't have to be pretty, but it does need to show how a customer connects to an order. If one customer has many orders, write down customer 1 N order on your paper. If a product appears in many orders and many orders have many products, mark that as product MN order. Continue this process until every relationship, like an order belonging to a business unit, is visible in front of you. This is where you find the gaps. Look for places where relationships should exist but are currently missing. If a support case belongs to a customer but your schema doesn't enforce that rule, you need to add it. If an invoice references an order but they aren't connected in the system, you have found a structural weakness that needs to be fixed. This exercise forces a level of clarity you can't get any other way. Take a critical process like order to invoice and map every entity involved, from the customer and product down to the shipping and billing addresses. Once you've drawn how they all connect, try to explain it to someone who isn't technical. If they can't follow your logic, it means your model isn't clear enough yet. Validation happens during that specific conversation. If you can't explain to a stakeholder why you need separate entities for order lines and invoice lines without saying it's technical, then you have failed the test. The model has to make sense for the business first, and the technical side comes second. The moment of true insight is when you realize your current model actually contradicts how the business works in the real world. You might find that finance and sales use completely different definitions for revenue, yet your model treats them as the same thing. That isn't just a schema problem, it's a fundamental business problem that your data model is finally revealing. That is what success looks like. You aren't searching for a perfect model that never changes. You are looking for a model that makes your business assumptions explicit so you can finally discuss whether those assumptions are actually correct. The final checkpoint is simple. Can you explain this entire model using only business concepts? You shouldn't need technical jargon because these entities represent real things the organization cares about every day. Skill development path. Logic delegation. Learning to delegate logic starts with an inventory. You need to know where your logic currently lives and whether it actually belongs there. Start by auditing your Power Automate flows, every single one. Don't just say it's an automation. Ask what the work actually is. Is it a validation, a calculation, a notification, or is it orchestration? You have to categorize these ruthlessly because the location determines the performance. Validation and calculation are your primary candidates for migration. If a flow reads data, evaluates a condition, and makes a decision based on that result, that is validation. Validation belongs on the server. If a flow pulls values from related records and combines them to get a total, that is calculation. Calculation also belongs on the server. Notifications and orchestration, however, should stay exactly where they are. If a flow sends an email, posts a message to Teams, or calls an external API, keep it in Power Automate. Flows are built for that kind of communication, and they do it well. When you start the move, look for the high-volume candidates first. Find the flows that trigger thousands of times every day, because those are the ones where server-side migration creates a massive compounding performance boost. Pick one simple task to start with. Maybe you have a flow that checks an order amount against a customer's credit limit. That is a pure calculation, so move it into Dataverse by creating a calculated field. Set your formula so that if the order amount exceeds the limit, the field returns a warning. Once you deploy and test that the field calculates correctly, you can measure the actual impact. In the old model, validation only happened when the flow triggered, but now it happens the moment a record is created. There is no flow to wait for. There is no latency. It is just data. Once you have done this once, you understand the mechanics of the new pattern. The logic lives in Dataverse now, and the app simply reads the field value without any extra processing. Don't try to move every rule at once, because that is exactly how migrations fail. Pick the validation logic in your most critical path, move it, and watch it work before you touch the next one. The transition period is where you protect the system. Keep your old flow running while you build the new logic and let them both run for a full week. Compare the results to ensure the server-side version calculates identically to the old one. Disable the flow, but keep it in the environment for 3 months, just in case you need to revert. The final checkpoint is defensive. You should be able to explain exactly why each piece of logic lives where it does. If you moved validation to Dataverse, the reason is that server-side execution is instant. You aren't waiting on network latency or external services anymore. The answer shouldn't be a guess. It should be a structural fact. Changes become much easier once your logic is centralized in one place. If a credit limit rule changes, you update the calculated field once, and every order respects that new limit immediately. This doesn't happen because flows are synchronizing data. It happens because the rule lives in the data itself. The maintenance burden drops the moment you stop hunting through 50 different flows to find a single rule. Skill development path, security architecture. Designing security architecturally starts by looking at what you have and asking why it exists. Map out your current access model. Don't think in general terms. Get specific. Create a table that lists user roles, the tables they can access, and the specific columns they can see. The simple act of writing this down usually reveals where the system is broken. Now ask the hard question, is this access based on a job function, or is it just based on history? If a user has read access to every case in the system because they asked for it once, that isn't security, that is an accommodation. If their job actually requires seeing every case to perform a task, that is a function. You have to distinguish between these two ruthlessly. Next, identify your security gaps. Look for places where people are seeing data that should be private. If a support case contains salary information that is visible to staff outside of HR, you have a gap. If accounts belonging to specific regions are visible to everyone in the company, you have another gap. Document these gaps before you try to fix them. Map the natural boundaries that already exist in your organization. Think about business units, departments, and geographic regions. In a healthcare organization, regional offices manage their own cases, which creates a natural data boundary. Your data structure should respect those boundaries. When you design the role structure, focus on actual job functions. Don't just copy a standard template because it's easy. A salesperson needs to read accounts in their territory, along with contacts and opportunities. A manager might need those same permissions, plus the ability to create new accounts. A field rep might only need to see their own assigned cases. Every role should be a direct reflection of a function. Now, build the relationships. A role grants a permission, and that permission defines an action like create or read on a table. The scope determines who they can see that data for. A salesperson has a read permission on opportunities, but the scope is territorial. The logic follows a clear path: user to role, role to permission, and permission to table. This exercise forces you to do a reality check. Try designing security for a new business process from scratch. If support tickets need to be segregated by region, you'll need a region field on the case and a role with regional scope. Diagram this out before you build anything. The diagram will show you exactly what you need before you waste time in the tool. The checkpoint here is forensic. If an auditor asked you to prove why a specific person can see a specific piece of data, could you do it? You should be able to draw a straight line from their job function through a role definition to their permissions. If that explanation is messy or confusing, your design isn't ready for production. Security becomes much easier once it is structural. When a new user joins the team, you assign them a role, and they automatically see the cases for their unit. You aren't setting individual permissions on records because the structure is doing the work for you. Changes are safer in this model. If a credit limit rule moves to a calculated field and you need to hide it, you just apply a security profile. The model supports the change because it was built into the foundation, not bolted on as an afterthought. The patterns that scale. Pattern 1. The master data model. Large organizations eventually realize they all need the same thing. Canonical data entities. These are core business concepts defined once and used everywhere. Take the concept of a customer. In a massive company, you might find customer defined 5 different ways because sales has their version while finance and operations built their own. Each team created a definition that matched their specific needs, but the result is 5 separate tables doing the same work. This leads to data conflicts and reconciliation nightmares where updates made in one system never reach the others. The master data model flips this logic. Customer is defined once for the entire organization rather than for a single department. It includes every attribute and relationship the business cares about in one single source of truth. This same rule applies to your products, orders, and contracts. These aren't just tables in a database, they are the way your organization actually thinks. When you build a new app, you don't redesign the customer entity from scratch. You simply extend the master model or add a single field if it's missing. The real benefit here is velocity. If a new sales tool needs customer info, you don't spend 3 weeks designing a schema and building relationships. You spend 1 week wiring it into the existing foundation. Building becomes faster and data quality improves automatically because every app is looking at the exact same information. But there is a risk. If your master model is wrong, then every single thing you build on top of it will be wrong too. This approach requires serious discipline and intentional design. You can't rush it. The upfront investment is much higher, but the payoff down the road compounds. I saw this happen with a mid-market company that had 50 power apps running at once. Every single app had its own customer table with different fields and different rules. When they finally moved to a master data model, they merged 12 different versions of customer into one entity. Development time for new apps dropped from 6 weeks down to 2 weeks. Data quality jumped 40%, not because the apps were better, but because the redundancy finally collapsed. Don't try to do everything at once. Start with your most critical concept, like customer or product, and get the business to agree on a design. Deploy that first, then move to the next one. Pattern 2, the transactional outbox. Data integration usually fails quietly. It doesn't scream for help, it just stops working. You create an order record in Dataverse and expect an event to fire so your warehouse stays updated, but the event gets lost in transit. The warehouse never sees the order. Days go by before anyone notices the mismatch, and by then, your other systems have already made decisions based on bad data. The transactional outbox pattern exists to stop this silent failure. The logic is straightforward. Every time a critical record changes in Dataverse, the system writes a new entry into a dedicated outbox table. This write happens inside the exact same transaction as the data change itself. Either both of them succeed or both of them fail. There is no middle ground where your data updates but the event record vanishes. Later, a downstream service checks that outbox table at regular intervals. It picks up each entry and processes it. Once the work is done, the service marks that entry as complete. If the processing fails for any reason, the entry stays in a pending state and the service simply tries again later. Eventually, every single integration is guaranteed to fire. The pattern is simple, but the impact on your architecture is massive. Your integrations become reliable without you having to build custom orchestration logic for every single move. You don't need to bake complex retry loops into every individual flow because the structure of the pattern handles the heavy lifting for you. I saw this play out with a retail company that kept their order system in Dataverse. When a customer placed an order, that data had to reach the fulfillment center, the accounting software, and the shipping provider all at once. Without an outbox, things were constantly falling through the cracks. They would have an order in Dataverse that never made it to fulfillment, or a package would ship but the customer was never billed. It was pure chaos. Everything changed when they implemented the transactional outbox. Now every order change writes to that outbox table in one clean transaction. Downstream services read the table, process the orders, and mark them finished. The mysterious gaps in their data disappeared overnight. To build this, you only need one extra table called outbox. You'll need columns for the record ID, the record type, the operation, a timestamp, and a processed flag. When a record changes, you insert an entry, then you just set up a flow or an Azure function to read those unprocessed entries and handle the rest. Pattern 3. The saga pattern for distributed transactions. Modern systems don't live in a vacuum. An order isn't just a row in one database. It spans across Dataverse for your CRM, an ERP for your inventory, and a separate billing system. Because these systems are distributed, a traditional database transaction won't work across those boundaries. You can't just hit save and expect 3 different clouds to stay in sync. The saga pattern is how you manage this complexity. It breaks a large process into smaller individual steps that target different systems. Crucially, every step has a matching, compensating action. If you get to step 3 and it fails, the system automatically runs the compensations for steps 1 and 2 to undo what they did. Think about a customer placing an order. In step 1, you reserve the inventory in your ERP. If that works, step 2 creates an invoice in the billing system. If that also works, step 3 creates a fulfillment record in the warehouse. But if that warehouse step fails, the compensation kicks in. It cancels the invoice and releases the inventory reservation. The customer sees a clean result because the order either succeeded everywhere or it failed everywhere. This pattern does require high observability. Every step has to log exactly what happened, so the compensation logic knows what to undo. You also need a correlation ID for each Saga instance, so you can trace the path of an order as it moves across your different systems. Your compensation steps must also be idempotent, meaning if you run them twice by mistake, the result stays the same. In a Dataverse environment, you usually implement sagas using a workflow orchestrator. You might have an Azure function watching a saga step table in Dataverse. It reads the pending steps, calls the external systems, and logs the results. If any system sends back a failure, the orchestrator triggers the compensation steps immediately. The real benefit here is reliability. In a world where systems are scattered, you aren't pretending that transactions work across different platforms. Instead, you are acknowledging those boundaries and designing a system that respects them. Your compensation is explicit, your testing is easier, and your debugging is finally clear. Pattern 4. The normalized reference data strategy. Reference data is the glue that holds your entire system together. Think about status values, country codes, product categories, or currency definitions. These small data points show up in almost every table you build, and how you handle them determines whether your system stays consistent or falls apart. The weak approach is to simply copy reference values into every table that needs them. You store a status as a text field in your orders table, then do it again in cases and again in invoices. Eventually, different values start appearing in different tables for the exact same concept, and the result is total chaos. The better pattern is to define canonical reference tables where each concept, like a status, lives in its own single source of truth. When a column needs a status value, it uses a lookup to that specific table instead of a manual text entry. This means you can change a status name in one single place, and it instantly updates across your entire environment. I saw this play out in a real scenario where different departments used different names for the same thing. Sales called a record active, finance called it open, and operations insisted on calling it live. Because they had one dataset with 3 different names, reports couldn't aggregate anything because the values simply didn't match. Implementing a canonical status table forced everyone to align, and once active, open, and live all became a single active status, the reports suddenly started working. Building this pattern takes discipline because you have to identify these reference concepts early in the process. You need to create a dedicated table for each one, document the values clearly, and use lookups instead of letting people type into text fields. Once you've built this foundation, you have to enforce it during design reviews to ensure new apps use the canonical data rather than creating their own local versions. These patterns aren't new inventions, but they are proven methods for organizations that need to operate at a massive scale. The master data model speeds up your development, the transactional outbox makes your integrations reliable, and the saga pattern manages your distributed complexity. When you combine those with normalized reference data to keep your values consistent, you finally have the infrastructure that lets relational intelligence actually work. Case study 1. From chaos to architecture. A mid-market manufacturing company I worked with had grown much faster than their systems could handle. They had 200 power apps deployed across the company, but there was no central governance at all. Teams were just building whatever they needed the moment they needed it, and the outcome was exactly what you'd expect. Constant, unpredictable failures. An update to a customer table would suddenly break 3 other apps that depended on that structure, mostly because the developers didn't even know those dependencies existed. In another instance, a critical finance workflow just stopped firing because someone archived a lookup table without checking who was using it. Reports were failing silently every single day because underlying data definitions were shifting without any kind of notification or oversight. The diagnosis was structural, and the problem was that grid thinking had taken over the entire culture. Every team was thinking about their specific app in a vacuum, which meant relationships weren't mapped and redundancy was everywhere. Security was being applied inconsistently on an app-by-app basis, and the logic was scattered so thin that nobody could track it. They thought they had a technology problem, but in reality they had an engineering crisis caused by a lack of a shared model. Their first step wasn't a massive rebuild, but rather an attempt to understand the mess they already had. They audited all 200 apps to identify which core business entities were being touched, and they mapped out which tables held customer info, product data, and orders. That mapping exercise revealed that customer data was living in 17 different tables with 17 different structures. Some tables had shipping addresses while others didn't, and some tracked tax IDs while others used business registrations. The definitions were in total conflict, so whenever 2 apps tried to coordinate around a single customer, they were essentially speaking 2 different languages. The challenge was that they couldn't just flip a switch and shut everything down to start over. These apps were live, and the teams and customers were relying on them every minute of the day. The solution was to build a new, clean model alongside the existing chaos and migrate the data piece by piece. And they started with the customer entity by designing a single record that included every necessary attribute. They built out the proper relationships to addresses, contacts, and hierarchies, and then they picked the simplest apps to migrate first. By building those new apps on the clean model and letting them run parallel to the old ones, they could stabilize the system before moving the users over. Only after the new version proved it was solid did they finally decommission the old, messy versions. This parallel approach definitely took longer than a total rebuild would have, and it was certainly messier to manage two systems at once. However, it didn't break the live environment, and it gave the teams a chance to see the new model working before they had to commit to it. It gave the organization time to adapt, and they learned more about their own data as they moved. About 3 months into the project, the metrics really started to shift in a big way. Development time for new apps dropped from 6 weeks down to just 2, and that wasn't because the developers were working harder. It happened because the foundation was finally there, the schema design was finished, and the relationships were clear. Developers could now extend the existing system rather than building every single thing from scratch. Even a third-party integration that used to take 4 weeks of custom mapping was finished in 3 days because the common customer entity provided the link immediately. By the 12-month mark, production incidents had dropped by 40%. This didn't happen because the code was suddenly perfect, but because the redundancy had been collapsed. When a piece of customer information changed, it changed everywhere at once, so there was no longer a scenario where one app saw an old version of a customer while another app saw the new one. The big lesson here wasn't about achieving a perfect architecture right out of the gate. It was about being intentional with the architecture you do have. You don't need a flawless design before you start, but you do need the willingness to design on purpose instead of letting your structure emerge by accident. That gradual migration allowed them to prove the model worked, and that proof was what finally turned the skeptics into believers. Case study 2, security as a structural problem. A healthcare organization was managing patient cases across several different regions, and the reality of their situation was high-stakes compliance. The rules were simple. Staff in one region should never see data from another. To handle this, they set up Dataverse, built out their case management system, and deployed their security roles before going live. Everything seemed fine until an audit 6 months later uncovered a major violation. It turned out that staff in the northern region could see every case from the south, and the reason was a fundamental flaw in how they built the system. The case table had no structural boundaries at all, so when the security role said a user could read cases, it didn't specify which ones. They had tried to layer row-level security on top of a flat data model, but that kind of setup is incredibly brittle. When an admin made a small change to improve query performance, the security layer broke silently, and nobody noticed until the auditors arrived months later. The fix for this wasn't just writing a better security rule, because the real solution was restructuring the data to enforce those boundaries naturally. They started by creating specific business units for each region and made the region field mandatory for every single case. They designed new roles with a regional scope so that a case manager could only see files belonging to their specific business unit. By doing this, the relationship between the user, their role, and the data became a physical part of the system structure. This shift required a massive migration because the existing cases didn't have regions assigned to them yet. Every record had to be audited and classified, which brought up difficult questions about cases that started in one region but moved to another. The organization had to decide if a case belonged to the place it was created or the place where the work was actually happening. The audit forced a level of clarity they didn't have before, and once that logic was defined, the system could finally enforce it. They didn't just flip a switch. Instead, they deployed the new structure to a test environment first. They ran side-by-side reports to make sure the new model showed the exact same data as the old rules. The data migration took 3 weeks to finish, and they spent another 4 weeks on validation and testing to be absolutely sure. It was a slow and deliberate process, but it was also auditable and proven to work. Once the new system was live, the entire compliance process changed for the better. In the past, auditors had to manually check if complex security rules were working, which was a slow and exhausting task. Now they just had to verify the data structure itself. If a case sits in the northern business unit, a southern staff member simply cannot see it, and there are no exceptions or rules to double-check. The structure made it impossible for a violation to happen in the first place. By the time they were done, the organization went from 47 audit exceptions down to 0. This didn't happen because their rules got more complicated or better in a traditional sense. It happened because they used structure to make non-compliance a physical impossibility. Case study 3. Performance through relational design. A services company built a system in Dataverse to manage their consultants, tracking everything from project assignments to skill inventories and budgets. In the beginning, the system worked exactly like it was supposed to, and users could log in and run reports without any issues. But as the company grew from 400 consultants to 2,000, the entire system started to fall apart. Forms that used to be instant were taking 12 seconds to load, and some of them just timed out and crashed. When they looked into the problem, they realized the model was denormalized in a way that couldn't handle the new scale. Every time someone opened a consultant form, the system had to pull data from 9 different related tables at once. It was grabbing project assignments, skill inventories, and billing rates. And each one of those lookups added another join to the process. Running 9 joins on a single form for thousands of people meant the system was executing incredibly expensive queries every single time a user clicked a name. To fix this, they had to go back to basics and normalize the data by separating the entities properly. They treated the consultant as one entity and the skill inventory as another, recognizing that the relationship between them was a complex many-to-many map. However, they also knew that querying that relationship directly was exactly what was slowing them down. That's when they took a counterintuitive step and introduced denormalization by design. They decided to add a cached version of the most important information directly onto the main consultant record. This included the primary skill, the current project, and the billing rate for the year. They didn't do this because the normalized design was wrong, but because they realized that high traffic areas need specific optimization to stay fast. They set up an automated flow so that whenever a consultant's primary skill changed, the cached field updated automatically. This meant the consultant form only had to load 2 tables instead of 9, and the load time immediately dropped from 12 seconds down to 2. The denormalization was strategic and carefully managed, allowing the system to keep a single source of truth while using the cache for speed. Before they moved anything to production, they ran extensive load tests against both the old and new models. They measured every query and response time to make sure the cached data stayed perfectly in sync with the main records. Every change they made was measured and proven through data rather than just being a lucky guess. After the new system went live, they saw a 60% increase in how much people actually used the software. This wasn't because they added flashy new features, but simply because the system finally worked the way it was supposed to. Staff could actually get their work done without the frustration of waiting for a screen to load. The big lesson here is that relational design isn't just about having the fewest number of tables possible. It's about building the right relationships and using performance-aware caching whenever the system needs to move faster. The ROI of getting it right. The financial case for relational intelligence is straightforward once you are willing to actually measure it. It starts with development velocity. When your architecture is intentional, teams do not have to redesign the foundations for every new project because they can simply extend what already exists. A properly architected Dataverse environment means new apps take weeks to build instead of months, and that difference compounds over time. If a team ships 3 apps in a year instead of just 1, that represents a 100% increase in productivity, which is pure financial value. A 500-person organization running this pattern across multiple teams can see a 50 to 70% reduction in the time it takes to get solutions into the hands of users. You can translate those gains directly into labor hours. An architect working at $200 per hour costs the company $400 per hour when you factor in benefits and overhead. Saving just 1 week of architecture work across 50 new apps annually adds up to $20,000 in savings. When you look at a large enterprise building 50 new apps per year, you are looking at $1 million saved just by getting the design and schema right the first time. The maintenance burden is where the real money shows up. Relational design reduces rework by 40 to 60%, not because the code is better, but because you have eliminated redundancy. When customer data lives in one single place, you do not have teams manually reconciling 5 different versions of the same information. If your business rules live in Dataverse, instead of being scattered across various flows, you only have to change them once instead of 5 times. When security is part of the structure instead of being bolted on later, you stop paying annual audit costs to fix missing controls. Imagine an organization with 50 apps built on fractured schemas. They might spend 10 hours per month on each app just managing redundancy, syncing data, and patching security gaps. That adds up to 500 hours every month, or 6,000 hours annually, which means you are spending over $1 million a year just to manage the chaos. Data quality improvements also show up in how fast you can make decisions. If your operational data is only 85% accurate, which is typical for these messy systems, you simply cannot trust your reports. You cannot rely on automation because you are uncertain about the foundation, so you end up making decisions much slower. Normalized models push that accuracy to 95% or higher, which allows decisions to accelerate and automation to become reliable. While the financial impact of faster decisions is hard to quantify, even a 20% improvement in speed across an organization creates a massive compounding effect. Compliance also finds its way into the ROI calculation through avoided costs. Audit exceptions are expensive because every single one requires an investigation, documentation, and a fix. Architecturally sound systems reduce these findings by 80%, which is the difference between 47 exceptions and 0. Since each investigation and fix costs between $3,000 and $10,000, an organization with 100 exceptions is spending up to $1 million on remediation. If you reduce that by 80% through good architecture, you are looking at hundreds of thousands of dollars in avoided costs. When you look at the aggregate picture, a 500-person organization with $100 million in revenue can realize $2 to $4 million in annual savings. That is 2 to 4% of total revenue, which is not just a small win, but a major strategic advantage. To calculate your own ROI, you need to start with a baseline. Ask yourself how much time your organization currently spends on maintenance, reconciliation, and fixing mistakes. Document how many audit exceptions you see annually and how long it takes to build a new app from scratch. Once you implement relational design on new projects, you can measure the difference and see the specific ROI for your company. The hidden benefit is not found in a spreadsheet, but in your own career trajectory. Architects usually command 40 to 60% higher compensation than builders, not because they are smarter, but because they provide more value. When you shift from being a builder to an architect, you move from being replaceable to being strategic, and your paycheck will eventually follow that shift. The risk of not mastering these skills. The opposite is also true, and failing to master relational intelligence carries a cost that grows every single day. Organizations that lack this skill eventually hit a plateau. The research shows that enterprises trying to adopt AI and Copilot without strong data architecture only see adoption rates between 20 and 30%. Their AI initiatives run into the same old problem of garbage in and garbage out. You cannot train an AI model on unreliable data, and you cannot make confident decisions based on information that is duplicated or conflicting. The organizations that actually reach 80% adoption are the ones with architects who designed their data intentionally from the start. Technical debt accumulates just like high-interest debt on a credit card. Each new app built on a weak foundation adds more complexity instead of more capability, so you end up building workarounds instead of functionality. Integration logic becomes a mess, where flows spawn more flows and plugins spawn more plugins until you realize that changing one field requires touching 12 different places. Your development speed does not just slow down, it actually reverses, and what used to take 2 weeks to build now takes 2 weeks just to modify. Compliance risk increases every time you take a shortcut. Poor data structures force expensive audits because row-level security that is bolted onto a flat model usually fails. Audit teams find these exceptions, which leads to remediation and rework that costs the company time and money. We saw one organization go through 7 audit cycles with over 50 exceptions each before they finally addressed the structural problem. The total cost of those failed audits, including the investigations and the re-audits, ended up well into the 7 figures. Decision-making also slows down when you cannot trust the data. When the information is unreliable, you do not trust the automation or the reports, so you demand manual verification for everything. That verification takes time, which means you are making slower decisions just to feel confident. While confidence is a good thing, slow decisions mean you are missing out on opportunities that your competitors are grabbing. Talent retention starts to suffer as well. Builders get frustrated when they are constantly asked to build on top of broken foundations, and architects leave when they cannot convince leadership to fix structural flaws. You will lose your best people to organizations that have better architectures, and the cost to replace them is immediate and significant. The ultimate cost of failure shows up as emergency rewrites, compliance violations, and a lost competitive advantage. One healthcare organization had to completely overhaul their case management system after a major audit violation, which resulted in 18 months of extra work and millions in costs. That violation only happened because they did not design their security as part of the architecture from day one. The hard truth is that you cannot automate your way out of a bad architecture. You cannot just throw more tools at the problem or hire enough staff to manage the chaos through pure effort. Only intentional design can fix these structural problems, and relational intelligence is the only discipline that actually works at scale. Your first steps, the 90-day roadmap. Knowing what to do is one thing, but knowing where to start is where most people get stuck. This 90-day roadmap is designed to ground relational thinking in actual physical action. This isn't about a total company transformation on day one. It is a proof of concept to show that relational intelligence actually works inside your specific organization. The first 2 weeks are all about diagnosis. You need to walk through your current Dataverse environment, but you aren't there to judge the mess. You are there to understand it. List out your tables and ask yourself why each one exists and what specific business concept it is supposed to represent. Look for where data is being duplicated across multiple tables. In a typical sales organization, you might find tables for accounts, contacts, companies, and organizations. Every single one of those represents a customer-like concept, so you have to figure out which ones overlap and why all 4 exist in the first place. This audit is how you reveal grid thinking patterns in your own backyard. Weeks 3 and 4 shift into design. Pick one critical business process that touches multiple parts of your company. Order to cash is a classic choice for this. Map out every entity involved, like the customer, the product, the order, and the invoice. Ask how they relate and what specific fields each one actually needs. You shouldn't try to redesign the whole world. So just focus on this one process and draw a diagram showing those relationships. Get your stakeholders to validate it. The person running sales should look at the customer entity and agree it's what they need, while the finance team looks at the invoice and agrees on what belongs there. This design becomes your master template. Weeks 5 through 8 are for the pilot. You are going to build one new solution using that relational design you just mapped out. If your diagram showed that a customer relates to an order through a one-to-many relationship, then go ahead and build that exact relationship. Use it, create test orders, and see if the design actually holds up when you use it in the real world. You need to measure the difference here. Track how long it took to build this using relational design compared to your average project. Look for unexpected complications and see if the structure stays solid under pressure. Weeks 9 through 12 are about expansion. You take that same pattern and apply it to the next business process. Don't do everything at once, just do one more and then one more after that. You are building momentum and showing other teams that this approach actually works. As each new solution goes live, you need to capture the metrics on development time, data quality, and integration reliability. These patterns compound over time. By week 12, you should have 3 or 4 new solutions that prove relational design makes development faster. The 90-day checkpoint is simple. Can you show measurable improvement? You need to know if solutions built this way took less time to develop than your organizational average. Check if they have fewer bugs after launch and if your new integrations are more reliable. If the answer is yes, you finally have proof. That proof is what converts the skeptics. When you run into resistance, just show the data. Let the results do the talking for you. A team might complain that this design approach feels too restrictive, but you should wait until they try building on a relational foundation and realize they shipped 4 weeks faster. That is how a skeptic becomes an advocate. This investment is almost entirely about time. You don't need major new tools or expensive licensing costs, and you aren't buying a fancy data modeling platform. You are simply changing how you think. That costs nothing except the hours you spend doing it right instead of rushing. Building a center of excellence. A 90-day pilot proves that relational intelligence actually works, but scaling that success across an entire company requires a real structure. You need a center of excellence. But let's be clear about what a COE is not. It isn't another slow-moving governance committee or a group that exists just to attend meetings. It's a dedicated team that owns and pushes relational thinking into every corner of your organization. You need a core group to make this happen. This starts with an architect who understands relational design and can mentor others, alongside a data steward to manage quality standards. You also need a security lead focused on access and compliance, plus a business analyst who can translate messy business concepts into clean data models. The charter for this group is simple. They define standards, provide templates, and review designs to help teams move faster. This isn't about gatekeeping or slowing projects down. It's about enabling them. When the architect validates an entity diagram before a team starts building, they aren't there to say no. They are there to show the team how to think about the problem correctly so they don't have to rebuild it later. Because the COE provides templates, new teams never have to start from a blank canvas, and they immediately inherit patterns that are already proven to work. Your first major deliverable is an entity catalog. You have to define the core business concepts that everyone uses, like customer, product, order, or case. Every single one of these gets documented so everyone knows exactly what fields a customer record has and why those fields exist. This catalog becomes the ultimate reference point for the company. When a new project starts, the team references the catalog instead of wasting time creating their own local, disconnected versions of the same data. The second deliverable is a set of design templates. When a developer starts a new project, they shouldn't be guessing how to structure a hierarchical organization or how to set up a many-to-many relationship. They should have a template for that. These templates show exactly how to implement common patterns or design an approval workflow. This doesn't just ensure consistency across the board, it drastically accelerates the entire design phase. The third deliverable is governance, but not the kind you're used to. The architect reviews major schemas before they hit production to catch structural issues while they're still easy to fix. This isn't a sign of distrust, it's a way to spread knowledge. Every single design review is an opportunity to teach a team something new about relational thinking. The ultimate goal is to make relational thinking the default way of working. It shouldn't be a special process reserved for high-profile projects. It should just be how you build things. Eventually, teams will expect their solutions to be designed this way. They'll assume the entity they need already exists in the catalog, and if it doesn't, they'll naturally work with the COE to add it the right way. A center of excellence usually takes 6 to 12 months to really mature, so you have to be patient. This is a cultural shift, not a quick technical fix, and you should expect some resistance early on. The best way to handle that is to celebrate early wins and show exactly how relational design saved a specific team time. Invite the skeptics to your design review so they can see the logic for themselves, and over time, that resistance will turn into adoption. Measuring progress. You can't improve a system if you aren't measuring it. Relational intelligence is either succeeding or failing based on outcomes you can actually track. Technical metrics are the first thing you should look at. You need to track your development velocity by measuring how long it takes to build a typical app before you implement relational design. Once you measure it again afterward, the improvement becomes quantifiable and hard to argue with. You'll also see a shift in code quality, which shows up as fewer urgent changes after a launch and a massive drop in duplicate data issues. Business metrics are what your stakeholders actually care about. They want to see time to value, user adoption rates, and compliance status. These numbers connect your architecture directly to business results. When you can report that solutions built on a relational design hit production 40% faster, you're finally speaking the language of finance. Organizational metrics tell you if the cultural shift is actually sticking. Look at your architects. In the early days of a COE, talented architects often leave if they feel their advice is being ignored by the rest of the company. If your architects are staying and taking on more responsibility, it means relational thinking is becoming a reality. You should also check in with your citizen developers. If they tell you that building on a relational foundation makes their jobs easier, then the system is working. For the best results, you should measure your velocity every month to get quick feedback on whether things are improving or sliding backward. Business outcomes change more slowly, so those are better suited for quarterly reviews, while organizational health can be measured once a year. Where you share these results is just as important as the data itself. The Executive Steering Committee needs to see the financial impact, while the Architecture Review Board needs to see the technical patterns. Individual teams should see how their work compares to the rest of the company. This kind of open communication creates a natural sense of accountability. When it's time to celebrate, make sure you recognize the teams that are getting it right. Share their success stories and be specific about the hours they saved or the bugs they prevented. You want to make relational thinking visible as a badge of success, rather than a piece of bureaucracy. The final checkpoint is very straightforward. Are these metrics moving in the right direction? If they are, you aren't just talking about relational intelligence anymore. You're actually living it. Moving from grid thinking to relational intelligence is more than a technical pivot because in reality, it is a career transformation. You stop building isolated applications and start architecting integrated systems, and that shift changes everything about your value. Entity mapping, logic delegation, and security architecture are not just theoretical concepts to study. These are learnable skills that separate the architects from the builders, and the patterns that actually scale, like master data models or saga coordination, already exist for you to apply. Your first 90 days will determine your success, so you need to pick one business process and design it the right way. Once you prove the model works, the momentum starts to build itself. The organizations that master these skills will easily outpace competitors who are still relying on shortcuts. This isn't just a technical advantage, it is strategic positioning that creates real competitive distance. This is where leadership begins. It isn't about mastering buttons, it's about mastering the structure. Subscribe for deeper dives into Microsoft 365, Copilot, and Azure. Connect with me on LinkedIn and let me know which topics matter most to your organization right now. The foundation determines everything. Build it right.